Implementation of slab waveguide analysis. In this video, we're going to start getting into the part of computation and simulation that's much more of an art than a science. Things in this course so far have been pretty much cut and dry, but here we'll touch on the more artistic aspects. So first we'll discuss implementing slab waveguide analysis in MATLAB, and then we'll talk more about resolution on the grid and what we're calling spacer regions. Implementation in MATLAB. So implementation of slab waveguide analysis goes very much like this. We'll initialize MATLAB. At the very start of our code, we'll have something called a dashboard. This is where all of the hard-coded numbers go and anything to control our simulation. So we'll describe the materials, dimensions of the waveguide, parameters about our grid that'll control resolution and size of that. And no work happens in the dashboard. After the dashboard, everything is done relative to the dashboard and no more hard-coded numbers. You know you've done something wrong if you get your code working and you get an answer, and then I say, okay, but now let the width of the core region be 3 instead of 2. If you have to change more than that single number in the dashboard to do that, you've written your code wrong. And the reason that's important is because eventually you'll get to parameter sweeps where maybe I ask, plot the effective refractive index as a function of the thickness of the core. If you have to go in and change multiple things every time you change the thickness of the core, you're setting yourself up for a lot of work. Whereas if you write your code correctly, you just write a big for loop around the rest of your code and it works wonderfully. Okay, so outside the dashboard, we will calculate our grid, that's number of points, the resolution. We will build a device on the grid, so we have to somehow draw a picture of a slab waveguide on our grid. We will then perform the finite difference analysis. We will do convergence study sort of stuff. And when we finally think we have a correct answer, we will visualize the results. So you're going to see every line of code in MATLAB to simulate this slab waveguide using the techniques that we've been discussing. So first is the dashboard. Yeah, well, I like to start my programs with the name of my script file, slab demo. And of course, I like to initialize MATLAB. So we'll close all open figure windows, clear any text from the command window, and then the most important, clear all variables from memory. Now we enter the dashboard. This is where all of the hard-coded numbers are. We want to control everything about our simulation through the dashboard. No work happens here. So the first thing is we define the wavelength where we're operating the simulation, and that is a value of 1. And 1 what, you might ask? It doesn't matter as long as we use those same units anytime we define any kind of distance, which will be A and later B. So if this is microns, as long as A and B are also in microns, everything works out. So this could be whatever unit we wanted it to be. So that's the free space wavelength where we're analyzing this. Then we move on to the slab parameters, everything that describes our slab waveguide. So first we have the refractive index in the core. That's where the modes will be guided. And then we have the refractive index surrounding that. And I'm just forcing that for simplicity to be the same refractive index N2. Then we have the thickness of the core region, 3 wavelengths. And it turns out that's a little bit thick for a waveguide. And the reason I'm doing that is so that this waveguide supports multiple modes and we can calculate those and see them. Now we're going to move on to B, and this is what I call a spacer region, and it's how much of this stuff do we need? Well, remember, we're using Dirichlet boundary conditions at the edges, and we are forcing our function, in this case the electric field, to be 0. So we need to make sure that those boundaries are far enough away from our guided mode that our guided mode can decay and be 0 for a bit before it hits the edge. If we have those boundaries too close, we're going to get very inaccurate answers, and we'll see that when we discuss it later in this lecture. We then define NRES, and this is the number of points per wavelength for our grid resolution, and we set our grid resolution to our wavelength divided by NRES. So this will be a resolution of 1/10 of a wavelength. And we might ask, where am I coming up with this NRES 10? And right now, it's just a guess. What we have to do is look for convergence. So we will get our code working, we'll run a simulation, think we have an answer. Then we'll crank up that NRES to maybe 15 or 20. Then crank it up to 25 or 30. And we're going to watch the answer we get as we do that. At some point, the answer stops changing a whole lot, and we will call our code converged at that point. And so that's something that happens at the end. Very last thing here, we're defining the number of modes we would like to calculate and plot. And so we would like to calculate and plot 5 modes. Next step is building the device on our grid. So the first thing I like to do is calculate the physical size of the grid. And so that will be the size of our core plus 2 times b, right? Because we have a spacer region above the core and a spacer region below. So that's the physical size of the grid. Then I like to calculate how many cells wide or tall this grid will be. And that's the physical size of the grid divided by the cell spacing that we calculated in the dashboard. Well, this could come out to be a fractional number like 103.7. And how can we have a grid that's 0.7 points? We can't do that. So we round up. Now, if we've rounded up, our grid is potentially larger than what we calculated to begin with. So I just like to recalculate that. Even though I may not even use SX, big SX again in the code, I like all my parameters to be consistent. Then I'll calculate what I call axis vectors. This will be the center position of each cell in our one-dimensional grid. The first thing I'll do is create an array that goes from 0.5 all the way up to number of cells minus 0.5. So this array is going 0.5, 1.5, 2.5, 3.5, all the way up to the end, so that when I multiply by the cell size, now I have an array that is the center position of each cell. And then, not necessarily needed, but something I like to do a lot is center the grid about 0. So X will go, negative numbers one way and positive numbers another. That's just preference for aesthetics. That's not really needed numerically at all. Now I have to create an array and build my device, build the Slab waveguide into this array so that somehow we're drawing a picture of the slab. So here would be my 1D array, and I need to fill values in. And in this case, I'm filling in refractive index values. So I call this the stop-start technique, and here's how it works. We need to calculate the array index where the Slab waveguide will start and the array index where the Slab waveguide will stop. And then in a later step, we can go ahead and build in the array. So here's how that works. And we're going to center this. So I also call this my centering algorithm. So first we calculate a little nx. This will be the number of cells wide this A region is. So that's what little nx is representing. So I take the physical size and I divide by the cell size. Now this might come out to be a fractional number like 17.2. Well, we can't have 0.2 of a cell, so I'll round that. So we are making the closest possible guess as to the number of cells wide the core is. All right, given that, we need to calculate the start index. So that's where this slab will start. So array index 1, 2, 3, all the way up to, I'll call that 10 or something like that. So how do we do that? Well, nx, big NX divided by 2, that's the center of the grid. Then we subtract little nx divided by 2, so we're at the center of the grid, and we back up by half of the slab, and that gives us right where we need to be. That could be a fractional number, so again, I round, and that's the start of the guide. Now, I don't really need to be too paranoid about this specific calculation. The position of this core could be up or down a few cells, not a big deal at all. What is a big deal is that we calculate the stop index, so it's the exact correct number of cells away from NX1. So this thickness here is correct, but the position of that in the grid is not as correct. So where's the stop index? Well, it's the start index plus the number of cells wide that core is, and then we have to subtract 1, so we're not off by 1. So why is this here? Well, let's pretend for a second it's not. And let's say our core is 2 cells wide, and we're starting at array index 10. we would calculate 10 plus 2 is 12. Then when we go down here and build it, we're going to fill in 10, 11, and 12. We would have filled in 3 cells. And we don't want to do that because little nx was 2. We only want to fill in 2 cells. So we subtract 1, so we're not off by 1. So this calculates stop and start index to center this core in our 1D grid. Now we go ahead and we build n. So the first thing I'll do is I'll initialize it all to zeros. Now zeros is not a real number. Refractive index is never less than 1. So I like to initialize it all with zeros. So when I plot it, I can look at it. And if I see any zeros, I know I've goofed somehow. So I create a column vector. It's by nx by 1. It's all zeros. I will fill in everything up to where that core starts, minus 1, with n2s. So that's filling in all n2s in this region in the grid. Then I'll go ahead and I'll fill in from nx1 to nx2. I'm going to fill in with all n1s. So I've just filled in this core region. Then last, I'm going to go from nx1 plus 1 all the way to the end of the grid nx and fill it in with n2s again. And I could put all n2s here. Now I've built my core into that grid. An alternative way to do this would be instead of zeros here, say 1s, and then multiply it by n2 out here. So n2 times 1s, nx comma 1. That would flood fill this entire grid with n2s, and then I would only need this line of code to go ahead and fill in the core. I could do that just as well too. Okay, so at this point, we now have our grid and we've built our device on it. Now we're ready to perform our finite difference analysis. So first thing, remember we've normalized our grid, so we need to calculate our k0, that's the free space wave number, 2 times pi divided by the free space wavelength. To build our matrix X, we need our derivative matrices. This specific differential equation only has a second order derivative. So we start by initializing our derivative to zeros, and it's sparse. We never want any full matrices anywhere. So this gives us all zeros in a sparse matrix that is nx by nx elements. Now we're using the spdiags command, so sparse diagonals. This is the command in MATLAB that we can insert diagonals into matrices. And it has 3 input arguments here. This last input argument is the matrix that we want to insert diagonals into, and we're trying to build this dx2, so we keep giving it dx2. The second input argument is which diagonal we're inserting into. So first we're inserting into the -1 diagonal, so that's going to be inserting these 1s in the -1 diagonal. So positive 1s. Then the second line, we're going into the center diagonal with -2 times the 1, so -2s, and we're inserting the -2s. And then this third, we're inserting positive 1s again in the +1 diagonal, and that's the +1 diagonal here. And then the very last thing, we would divide by dx squared, but remember we have a normalized grid, and we've multiplied our spatial coordinates by k0, so we're dividing by k0 times dx, that product squared. And we see that out here, and that gives us our normalized grid coordinates. Okay, at this point, we've built our derivative matrix. Now we're going to build the diagonal n matrix. It still needs to be squared, but we're just going to build the diagonal n matrix. The first thing we'll do is reshape it to a column vector. We then declare that column vector as sparse because we don't want to ever build a full matrix. And then we use the diag command to insert that sparse column vector into a matrix, and MATLAB knows to make a sparse matrix with a diagonal. Yes, we could have used the spdiags command to do this just as well, but for some reason I like typing that in, and that's just what I do, but spdiags command would work just as well. Now we're ready to build this matrix A because we have our derivative matrix and our n matrix. So it's just the derivative matrix for the second order derivative plus our diagonal n matrix squared. Notice we're not saying dot caret 2 because that would be performing a dot by a point by point or element wise. We want to do a matrix squaring. Now this is a bit of an exception because n is a diagonal matrix, and it turns out an element wise and a matrix wise squaring would be the same thing. but we just want to use good practice, and we know if it's a matrix, not do the element-wise squaring. Okay, we've built A. Now we can call eig. And here we're cheating a little bit and declaring this full, and that's because I know this is a relatively small matrix, and eig likes full matrices. We could just as well call eigs, but the reason I'm doing all this is I know ahead of time it's a small enough matrix, and calling eig with a small matrix is faster than calling eigs, which is really the sparse version of eig, with a sparse little matrix. It turns out this is faster. So that's what I'm doing. And then that outputs the eigenvector matrix and then the eigenvalue matrix. And if you remember how we formulated our eigenvalue problem, our eigenvalues are the effective refractive index squared. So this is a diagonal matrix. So when I call diag on the diagonal matrix, that extracts the diagonal and gives us a one-dimensional array of the elements down the diagonal, which is effective refractive index squared. I'll then take the square root, and I get a one-dimensional array of the effective refractive indices of the modes we've just calculated. Now that everything's done, we can visualize the results with a fancy plot. And I won't go too much through this, but in other places in this course, I go through everything here that you could use to develop a nice fancy plot like this. But notice I've plotted the first 5 modes, and had I typed in m equals 10 in the beginning, I'd see 10 modes, although maybe it would start getting a little bit more cramped. But I'm labeling which one's which. Mode 1, 2, 3, 4, 5. I'm plotting the mode. I am plotting the effective refractive index of the modes, and I'm doing something else. Notice I'm putting a little white highlight around the line. And sometimes I like doing that when my line is going to cross both light and dark backgrounds so the line doesn't disappear. And that's easy. I just plot twice, once with a thick white line and a second with a thinner blue line, a second time. Real easy. And so the analysis is almost done. Really what I need to do now is start experimenting with resolution on the grid, spacer region, look for convergence, those types of things. And that's the type of stuff we'll talk about next. More about resolution and spacer regions. So in the beginning, I like to always create a very low NRES, so all my matrices and arrays are very small, everything runs quick, and I wait until it runs without error and I think everything's correct. At that point, before I conclude anything about my answer, I'll always perform a convergence study. So what I'm doing here is I am plotting all of the effective refractive indices for my 5 modes as a function as I crank up this NRES. So my grid is getting higher and higher resolution, more and more points on the grid, but of course, more memory is required. Simulations are slower, but hopefully I'm getting better and better answers. One thing I notice is that my higher order modes converge more slowly. So if I would like to only check one for a little bit less work, check your highest order mode. Also notice that the higher order modes have the smaller effective refractive indices. That's because they start sticking out into the cladding region a little bit more than the fundamental mode. So looking at this convergence study, I'm going to ask myself, where do these essentially settle into the final answer, and cranking up NRES really doesn't bias anything anymore. And I might throw out an NRES of 10 is about where things converge. Yes, I could get better answers if I cranked it up even more, but for my work, maybe an NRES of 10 would be good. If you're designing somebody's pacemaker, yeah, you might want to operate out here with an NRES of 30, but for some preliminary crude work, NRES of 10 here is pretty good. So never conclude anything from your simulation without doing a convergence study. That's absolutely critical. All commercial software always simulates a device many times, and what it's doing is its own automatic convergence study. Sometimes you'll hear words like adaptive mesh. It runs a simulation, refines the mesh, runs a simulation, refines the mesh, and it keeps going until the answer doesn't change much anymore and it's converged. So absolutely critical, absolutely critical. Now let's talk about these spacer regions. How big should we make B? And there's really not, even with being an expert in electromagnetics, I can't tell you how big to make B. I could tell you most of the time a nice healthy guided mode really doesn't extend outside the waveguide by more than a wavelength. But if we made B only one wavelength, that might still be close enough to cause some numerical errors. There's also some weird times where the field can extend very far outside of that core. So really, what's going on here? Remember, we use Dirichlet boundary conditions. That's going to force the electric field at either side to be zero. So really what we're doing is we're simulating something with metal on the outside. We're actually simulating a much larger waveguide. But we want to make sure that these B regions are large enough that, yes, we're still simulating a very large waveguide, but what we'll see is modes in that very large waveguide that are essentially confined to just the core. And that's really the modes that would be guided by just the core alone. So, and this is where the art of the simulation comes in. How big do we make B? And so sometimes we'll start small, we'll check it, we'll make it bigger, and we'll do a convergence study on the size of B. Here's a great way to visualize that. So here I am changing the size of that spacer region and bringing it closer and farther. And what you can see is not only the shape of the mode is changing, but the effective refractive index is changing. And the thing to notice here, as we go far away, at some point that change starts to stop and becomes minimal. And we see that effective index start to converge on a number as it gets farther away. And so based on this, at about a half a wavelength, it seems to be sufficient for that spacer region. So I might make it 1 wavelength or just stick with a half wavelength, just depending how good I want things to be. But if we goof on that spacer region, we still get N answer, and it might look right, but we'll only know that it's wrong if we make that spacer region bigger and we see that the shape and the effective index of that mode actually does change. So we want to make B big enough so that those changes are minimal. There are times where the field can extend very far outside of that core. And the field outside of the core are called evanescent fields because inside the core, the field can oscillate, but outside it can only decay. It can only be a decaying exponential. So yeah, we call those evanescent fields, and there are at least 2 conditions where we can get large evanescent fields where we need huge spacer regions. One is if the thickness of the core is very thin. And watch what happens when it becomes very thin. Suddenly, when it becomes like hair thin, we see that evanescent field go very, very far from the waveguide. So if there's a time where you want to do that, now we need very large spacer regions. Here's another time. We might be interested in some of these guided modes right near their cutoff. And here we're looking at a second order mode. And we're looking at that as we increase the wavelength relative to the size of that core. Or alternatively, we could have kept the wavelength the same and just pinched the size of the core down, but this is easier to visualize. So as the wavelength becomes larger relative to the core, at some point, boom, that's not a guided mode anymore. The core is just too small to guide that mode, and that's where the big red X's appear. But you'll notice right before those big red X's appear, that mode very near cutoff has very large evanescent fields. So if we're ever designing something that actually uses a mode very near its cutoff, well, we're going to need large spacer regions. So, you know, a rough rule of thumb of saying those spacer regions, normally that evanescent field's within a half wavelength or 1 wavelength. Well, that might work for a lot of times, but not all times. And we should always plot our answer. We should always do some kind of convergence study just on the size of those spacer regions themselves to make sure that they were big enough. So here's a convergence study for the spacer region, and I would call this converged at about a 1/4 wavelength. But of course, I'm not looking at modes near their cutoff, or I'm not looking at a really, really skinny core. It's rare that we would actually design a waveguide to operate in those areas, but I said rare, that doesn't always not happen. Sometimes we want to. Modes behave really squirrely near their cutoff, and we can use that to make sensors and other things, so they do have their uses. But I think for a healthy waveguide, it looks like a 1/4 wavelength spacer region is sufficient for us.